Welcome to our discussion of Pascal's Principle and example number 4. Let's imagine that we have a little cube here composed of the same fluid as the surrounding fluid around it. And we're going to assume that this cube of fluid here has negligible weight. And we'll also assume that this fluid is static, so it's not moving at all. We've been assuming all along through this section that we're not looking at moving fluids right now. Now there would be inward forces acting on the cube from all the different faces here, from the back and front and sides and top and bottom. And the forces from the front side and the back side would be equal, and the sides would be equal because they're all at the same depth. And we can extend this argument and say that really any size or shape of this piece of fluid, that the fluid pressure must be the same everywhere in a weightless, static fluid. So what this really means is that if you were to look at this example here, this is called a Pascal's vase typically. And if you were to look at this particular point here, number 1, and then another point directly across here at number 2, and another one directly across here at number 3, and another one here directly across at number 4, all of these connected vases, because this is really one fluid, would all have the same pressure if they were all the same depth, h. So what we're really saying here is that in a confined fluid, the pressure is transmitted everywhere throughout the fluid and is undiminished even along through these walls of the container. So this is all really one fluid in here, and so the pressure here, 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 and here are the same. And if I were to simply tilt the apparatus, you'll see that the level of the fluid would remain at the same place. So the pressure really only depends on the depth. The shape of the container makes no difference. They'll still have the same pressure. Even though this has a bigger cross-sectional area, it has the same pressure as it does over here at these other tubes. Now this principle is quite important in really the science of hydraulics. So when you need to get your muffler changed on a truck, for example, and it has to be lifted by some mechanism, it's called a hydraulic lift. And so you can see down here in the picture below, this is a hydraulic lift that is lifting up this vehicle here. The force that is exerted on the liquid by the piston right here with a relatively small area will cause a resulting increase in pressure over here on the other side, undiminished, because it's transmitted everywhere throughout this confined fluid here, and that will allow you to lift the truck up with that same pressure being at point A and at point B. Pascal's principle has many applications, such as hydraulic brakes in cars and trucks, and hydraulic controls in airplanes. There's a lot of various applications for it. So it goes back to really this, the pressure at the same depth. So if I were to look at this and say these are both at the same depth, so at point 1 and point 2 at the same depth, then the pressures are the same, so the ratio of their force per area is identical, and then we can solve the problem. So let's now look at example number 4. We have a hydraulic car lift with an input piston over here. So this is the input piston, and then it has a radius R1 of 0.012 meters with a negligible weight. So this little shaft here has a very negligible weight. And then R2 is the radius over here of the other piston of 0.15 meters. And the combined weight of the car and the plunger on this side is 20,500 newtons. The density of the fluid in here is given as 800 kilograms per meter cube, and we're asked to find out what is the force F1 needed to support the car and the output plunger when the bottom surfaces of the piston and the plunger are at the same level. So not this picture really, it's really the picture when they're both at the same level here. So let's maybe draw a new picture here for part A. So here's a redrawn diagram of part A. And according to Pascal's principle, the pressure increases the same amount at every point in the fluid. So really, this is kind of a proportion problem. This point right here we'll call number 1, and this point here we'll call number 2, and we can say that the pressure at those two places are the same. So pressure 1 and pressure 2 are the same. So then the ratio of the force per area, force 1 to area 1, are the same as force 2 to area 2. And then we can substitute in our area as pi r1 squared equals force 2 over pi r2 squared. The pi's can cancel out, and force 1 would be equal to r1 divided by r2 quantity squared times force 2. So let's go substitute in now. R1 is 0.012 meters, and R2 is 0.15 meters, and that's going to be squared, multiplied by the combined weight of the car and the plunger, which is 20,500 newtons. And this comes out to a force of 131 newtons approximately. Okay, let's move on to example part B of this. And now the plungers are not at the same level, but there's a height difference of 1.1 meters now. So in this case, you're still utilizing Pascal's principle. We're still going to assume that the pressure at A is the same as the pressure at B. However, pressure at A now includes this extra bit of weight of this fluid. So we have the force per unit area of F1 over pi R1 squared, plus you have this additional hydrostatic pressure, which is rho GH. And that's going to be equal to the pressure at B, which is the weight of the plunger and the car together divided by pi R2 squared. And in this case, you can't cancel out the pi's because of this term, and you're solving for the force once again. So F1 equals, and you need to solve all the way through this. You just need to substitute the numbers in. And there's my rearranged expression, which gives you the following expression. And then when you plug that all into your calculator, you should get 127 newtons roughly. And that's it for example number 4.